Thank you for having me. Has anyone done any computer vision before? Anyone? Yep, a couple of people. Has anyone wanted to? Yep, lots of people. Cool, well that's a good start. Alright, so I'm Alex and my background is mechatronics. So for those of you who don't know, it's kind of a combination of software, mechanical engineering and electronic engineering. So I kind of went down the path of software, so kind of out of there and then a little bit into there. And I kind of overlap a little bit sometimes, but I try to stay most in software and intelligent software and computer vision and that kind of thing. I find that great products have great software and that's what really distinguishes good hardware. So mechatronics isn't just about robotics, that's the obvious application, but I guess the main challenge for robots is to see and interact with the world around them. So the way that you do that is with computer vision if you're using a camera. So there's also more to computer vision than just killer robots. They're applying computer vision now to consumer products like autonomous cars. We have things like intelligent ovens, which think like a chef. They cook your food perfectly by knowing that there are cookies inside your oven. So they'll send you photos from the camera inside your oven, and all very clever things like that. There's a lot of other really cool applications in industry. So this is the one we'll be talking about today. And this is a robot out of Japan that is a strawberry picking robot. So for today's demo, I thought we would go through the algorithm involved in discovering whether a strawberry is ripe and locating where it is. So we'll start with something pretty simple. It's just finding a red blob on this image to start with. So we have some interesting challenges. There's a red blob down there that we have to ignore. There's an unripe strawberry next to it, and there's a big red strawberry, in case you missed it, right there. Oh. All right, so we're going to be using OpenCV today, and has anyone tried to install OpenCV before? Successfully? Yeah? Anyone unsuccessfully? No? Everyone's, yeah? Okay.
This was years ago.
Yeah. Well, it's much easier now. So if you're on a Mac, like most of us maybe, all good, then you'll be using Homebrew, or you can make it by hand if you really want to. Otherwise, if you're on Windows, you can use Conda. If you're on Linux, then I'm sure you're used to compiling things from scratch, so you'll be fine. There are a bunch of, this is the repos here. There's a bunch of Python samples, which are a good place to start. Or you can check out my repo, which will be at the end. And there's also some contrib stuff. So this is more stuff that doesn't get in the main one, so that they can't for licensing reasons. And there are a bunch of other things. So this will include all that stuff. This is if you're doing GPU stuff, which is like what I do at work. Video stuff, more video stuff, and Python 3 for those of you who made the jump. Most of you on Python 3 now? No? 2? Some? And a dabble?
Yeah.
Yeah?
Seriously, bring the shirt for it.
Yeah, the only one. Okay. Oh, cool.
Isn't there like a wall of shame for projects that haven't upgraded yet?
The name changed. It's now the Wall of Superstars. We try to be inclusive here.
Cool. So to start with, all we have to do is load in an image. So you give it a file name and you get its matrix. And the matrix is 1400 pixels high by 2100 pixels wide, and there are 3 channels. So you get this thing, you might recognize this. This is a NumPy array. So if you're used to dealing with NumPy matrices and things, arrays, this will make a lot of sense. So it's an unsigned 8-bit integer, so that means the numbers are valued from 0 to 255. And we have blue, green, and red. I don't know why, but they've gone with BGR rather than RGB. But it means that basically your image is set up like this. Yeah, could be it. And then we can convert between color spaces. So if you want to make it RGB, because you're used to RGB, you can do that. And then if you want to resize it, you can do either the destination size that you want, or you can scale it by a particular factor. So you can put in 2 and a doubled size. So once we have it, we can show it. So if you want to display it with a window like this, then you'll have to convert it back to BGR or whatever color space, from whatever color space you're working in into BGR, and then you'll have to show it and then wait for a key press. And if you don't convert it and you display an RGB image, you'll get the color channels swapped around. So if your images are much more blue than you expect, that's what's gone wrong. And there's a bunch of other GUI things that OpenCV offers. So you can do trackpad, like track balls, I don't know if that's right, mouse and keyboard kind of interaction, which is kind of cool. And then if you're using IPython or Jupyter notebooks, you can use matplotlib inline, and you can use all the matplotlib plotting stuff and just use a figure of whatever number of inches you want, and then show it. And that will look like this. And I've just wrapped that in a short function to make it a little bit easier, which is that guy. So that's just showing an image of any size, and you can see the dimensions in pixels down the bottom. So it's about 450 by 700-ish pixels that we've been working with. That makes it nice and convenient. And then we can just do some blurring. And this is pretty simple. It's just a Gaussian blur of 7 pixels in both directions. And we'll show the image again.
Yeah.
Yeah?
Why do you need to resample it in the previous throwback?
Yep.
You keep telling how to interpolate.
Oh yes, that's just to show it to the screen. So if you're making it bigger, you don't necessarily want it to interpolate.
Because
It's just
it will
a...
take the feed size, use the DPI to get the pixels and
Yeah, that's right. It's just a...
we'll try to feed in that one, okay.
Yeah, that's right. Yeah. If you're downsizing, you'll probably want to use a different interpolation method, and you can use cubic and that kind of thing. But nearest is pretty easy. Yeah, it means that if you have a really small image and display it big, it won't get really blurry, which is pretty good. It means you don't make mistakes. So basic image operations: we have blurring, we have cropping. So since it's a NumPy array, we can use the slice syntax. So from 100 to 300, which is this area there, by 200 to 500, and you get that. And that's pretty easy. It just returns that. And you get all 3 channels as well, because we've ignored the third bit. But if you want to look at just a single channel, then you can do this. So this is just a quick example. We can stack all the arrays together with NumPy again. That's just a V-stack. And then we get the red, the green, and the blue channels kind of displayed separately, because we're zeroing out the other ones. So, yeah. Does that all make sense so far?
Are these slides going to be online?
Yep. They're all on GitHub. They're using LFS, so everything's in the same repo. It's all nice and easy. And we can also display histograms. So histograms are really useful if you've done any stuff in images before. If you're a photographer or you've opened up Photoshop, you'll see these guys. This just shows you the frequency, how many pixels in the image have a particular intensity in each channel. So you can see that there's some bright red stuff, which is the stuff that we're looking for. And there's some green, probably from the background, and you can see where those areas are. So not much green on the strawberry, a lot of green, a lot of red there, and some kind of darker blue. I've simplified the code a little bit at the top, but it's basically just calculate a histogram, and you give it the ranges and stuff. The docs are all pretty easy, you can figure it out. All right. And the full code to generate all these plots and stuff is in my Python notebook. So if you want to see exactly the way I did that, that's all there. So our goal is to find the strawberry, but it's kind of hard to do that by using RGB. If you've played around before with RGB, you'll know that red is 25500, or in this case, it's 70%, 20%, and 15% if you're using percentages. But you'll also have other areas that are similarly high amounts of red, but they'll just have green and blue mixed in. So it's kind of difficult to figure out what's mostly red or a particular color that you're targeting. So you can see down there that we have similar numbers, and that's through an array over here. So RGB isn't a great way of doing that, but HSV is really well suited to that. So this is a color space. It's kind of how people view them. Have you worked with color spaces before? Yeah? Everyone knows HSV? Or no one? No one doesn't know it? Basically, the color is an angle around your cylinder, and then your saturation and value show how much gray and how bright your color is, essentially. So instead of redness, blueness, and greenness, we can use the hue, and we can try and find an area that's kind of around there. So we want to find, that kind of slice of the cylinder, and that's pretty easy. So if we look at the HSV, we do the same kind of thing, but we convert it first into HSV. You can see that we're using 2.5 instead of 0, like the other example. Basically, this is the hue only channel, with the other guys set to 1, so you can see exactly that this is pure red and that's pure green. And it's a really easy way to distinguish the red from the green. So that's a lot simpler and a lot clearer than that guy, which is kind of hard to distinguish. There we go. And same kind of thing, you if you're working in HSV, you have to convert back to RGB to show it again. And we can view histograms. So our histogram, you can see that the color hue along the bottom there goes from 0 to 180, and we're looking for a region that's at the right up there. So we want to find the red bit, so about 0 to 10 hue, and also 170 to 180 degrees up there. And we want to find a nice bright region too, so we'll do kind of a high saturation, a high value. That's being distracting.
You're doing great.
Thanks, man. So you basically just figure out all the colors in a particular range by using the in-range function. And you go from a minimum set of colors to a maximum set of colors. And you get this thing that looks like that. So it's pretty easy. This is a binary image. So for those of you who've done computer vision in the past, you're pretty familiar with binary images. So this is just all the colors in the image go between 0 and 255, and it's a single channel. So we don't have red, green, and blue, we just have black and white. And you can see that if we put them side by side, that's pretty much what we're looking for, but there's a couple of extra little bits, and it's a little bit incomplete. So if we do the 170 to 180 degrees in hue, you get the inside bit, which is the kind of pinker region. And then, since they're arrays again, and they're separate, you can just add them together. So we just take the first mask and add the second mask, and then you get this one. And you can see again, that's just a single UN, and they're all 0 to 255. And we picked up some of that right down the bottom right. Everyone following? So this is our result, but you can see that we're still missing some specs. This might have been the seeds, they're a little bit green. We're not sure exactly what was there. There's some other reddish stuff around. So what we need to do is use some morphological operations. So this is something we learned in computer science in uni. And it's basically, you take your original image and you apply some small kind of kernel. And you take your kernel and you move it around the outside or move it along. And where the kernel hits an edge, it will either erode, so make it smaller, or dilate, make it bigger. So you can see that since we've got something that's bigger than this bit here, we've eroded away the little tails there in the erosion, and dilation makes it bigger, and that fills in these gaps in front. And then if we erode, then dilate, we get an opening. So this is a different kind of function that combines the two. And then the other way around, doing dilation, then erosion is a good technique for closing. So we get the same size image, it just has all the gaps filled in. And if we apply that to ours, which is pretty easy, you create a structuring element of a particular size. There's an ellipse, or a rectangle, or a plus, or a bunch of other different shapes that you can use for specific things. And then you just apply it, and you choose your operation. And there are quite a few morph underscores you can just look through, and it's pretty easy to find.
So is that a 15 by 15 pixel ellipse?
Yeah.
Okay.
And when you're going through this, are you just like trial and error? You just try one and see what it looks like, and you know which one to use?
I guess, yeah, if you try a few, then you'll get an idea of which ones to use in different situations, but it's pretty easy to try, and you can, if you make something that's modifiable, you can just keep running it, and you can run all different sizes and
So do you
see
do
what
that
looks
in
good.
Notebook?
Yeah, I did in this case, yeah.
Right.
Yeah. You can also do it based on the sizes of your images and the shapes that you're after and that kind of thing, but yeah, whatever works for your problem. And then you can see that we've got our circle, which is that size there. We've eroded away all these edges here, and we've dilated them here. So there are two different ways that we could do this. And you can see that dilation looks a little better, but we've got all these blobs that are extra. And erosion, we've got rid of these specks, but it looks like someone's shot holes in it. So that's not great. And then if we do an erosion, then dilation, we go from there and then we expand it again, but we've lost the shape. Whereas here, if we dilate it and erode it again, then we filled in all the gaps, but we've still got a couple of specks. So what we can do is just combine them again, and then we go from the original, we close it, and then we open it again. So we get rid of all the specks and we filled in all the gaps. So it's a pretty powerful technique for just manipulating binary images. And a lot of companies do this for getting the edges of train pantographs and that kind of thing. If you happen to work in the braille industry, you know what I mean. Yeah. I'll be famous on YouTube. We'll see. So what we can do now is we basically do MS Paint's flood fill operation. So we want to fill in this and figure out which of these are continuous blobs, and this is called a contour. So all we do is return a list of simple chain. That's the technique that we use for using fine contours, but it's you can read about the other ones if you're interested. There's a whole bunch of different ways that you can figure out objects that are inside each other. So if we had a gap, we could find out all these contours that have smaller contours within them, and we'd get a tree. But since our case is pretty simple, we just that one. And then you can see that we're getting two contours. And the contours are actually this a set of points that surround this shape. So if we wanted to, we could make it a bit simpler. And we could turn it into a smoother strawberry. But in our case, we're just going to find the biggest one by using its area. And we can take the max of that, grab it out again, create a new blank black image. So that's just making a bunch of zeros in an array that are a particular shape and that type. And then we just draw it again. So here we're saying draw all the contours that we passed in, use white, and fill it in completely. This is the width. So if you set that to 10, you get an outline instead. But for our application, we want to find the center of mass, maybe, if we want to have a robot pick it up. So we're going to do that. And then you can see from the previous thing, that's basically got rid of our spec down the bottom. So that'll get rid of all the things that are, not the largest in the scene, which is what we're after. So if our robot wants to find the biggest strawberry, it'll always go for the biggest contour, and then once it picks that, it can go for the next biggest, and so on. So pretty simple.
Alex, you can defer this question to the end because it's a bit of an open discussion, but from the code, it doesn't look very Python-y, so I'm assuming just because
you could just replace key with CV to the auto area and then kill that entire line in half if you're indexing that.
Okay, it looks like maybe we'll answer at the end. I was just going to say, so I know OpenCV is obviously a C project.
Yes, that's right.
When you're looking for documentation and things like that, do you find yourself reading the C stuff and then trying to munch it into Python, or does PyOpenCV have enough docs that you can live in your own little Python world and not have to worry?
What's PyOpenCV?
Well, this is okay.
That's the answer.
Yeah.
Okay, right.
No, so it's all the same documentation. There's C, C++, and the old C++ API and the Python API, all in one. So when you read about a function, it's the same syntax. So you have your source, your destination, you use pointers and that kind of thing. A lot of the functions aren't particularly Pythonic, which is a bit of a shame. You can see we're using enums from C. We're passing in lists of stuff, and rather than using true or false or keys or whatever, keyword arguments, we've just passed out. It works.
Right. So like you said, this answers my question. Does that mean PyOpenCV makes this more Pythonic?
I don't think PyOpenCV is a thing, is it?
I just read PyOpenCV.com. Anyway,
Okay,
sorry,
maybe, yeah. Maybe that's a new project. I've never used it, so.
If you are familiar with
with the image processing tool in MATLAB,
Yeah.
and you can read the documentation easily, like an image read.
Yeah.
So all these names, they inherit from MATLAB.
Right, okay, right.
Yeah. That's a good point, yeah. There are other Python image processing libraries, but I find that OpenCV is the most advanced. And
It's a thing that you probably don't want to use it if it's on Google Code.
Oh.
And it hasn't been updated since 2010.
yeah,
Not recommended.
yep, agreed. Yeah, so you can actually run the same, a similar kind of thing, pretty much exactly the same function call, just with some types and stuff in C++ and C, and it'll work. So if you're moving between Python and C++ like I do at work, it's pretty handy. But yeah, you'll probably, you won't get a list returned. There'll be a second parameter you pass in to get your destination array and that kind of thing. So a bit more complicated. And then if we want to see what our mask look like on top of our background image, you just use add weighted. So you can add two images together and you use 0.5 for each and you get this nice effect where you can see what your mask is. And you convert it back from grey to RGB so that you can add the two together. And then we have our final result, basically. So if you remember your physics, you get the moments of your blob, your contour, and you can figure out where the center of mass is by these guys. And then you can draw a circle, and this is a beautiful API for drawing a circle. And then we can also draw an ellipse, but you have to use a contour for an ellipse instead. So basically you just pass in what shape you want to draw. There's ellipse, rectangle, and a whole bunch of other things. And then we have it. So the whole code isn't actually that complicated. Like, we've broken it down into steps, but you can see that basically we just load it in, we do some color operations, we find the masks, do some filtering, and then we have a little bit of cleanup. We find the biggest one, and then we overlay it and we can circle it. So all up, it looks like that. There we go. So now that we've made it work on one image, we can try it on a bunch of others, and you can see that it works pretty well. It picks up most of them. It's kind of ignored that one, which isn't very ripe yet. These are some kind of easy examples. If we try a few more advanced examples, you can see that we've got this guy, which was there. And here is the biggest by number of pixels. Maybe not by mass, but who knows. And then if we try some more challenging examples, you can see that I found a how-to article on stories. That hasn't worked very well. So the how-to orange. So if you're building a robot, maybe to put like orange banners behind. But obviously you can filter that out. If you know the exact hue, that's pretty easy. Or if it touches the edge of the image, you can filter it, that kind of thing. So yeah, you can see here we joined two together in a love heart. And we've missed the tip of that one because it wasn't ripe enough. Yes.
Get a blood stain on your overall or something.
No. Get grabbed out. Yeah.
Alex?
Yep.
Two things. Number one, we have a cup of coffee a couple of years ago.
Talking about sharks?
Yes.
Yes. Yeah.
That approach you've just described there,
Yep.
what's the advantage, disadvantage versus, say, sliding windows on your network and that sort of thing?
Simplicity, basically. Yeah, so you don't have to train a whole bunch spend your life circling strawberries and training a neural net to do what you can by just figuring out what color it is. I try the simple approach. If it doesn't work, use a neural network. There are lots of other approaches that you can do, from just basic colors to cleaning up to texture recognition to relying on the existence of seeds and that kind of thing, all the way up to training large volumes of data. Yeah. Well, that's it. It's my time. So the talk, a couple of example IPython notebooks. We even have a video demo, which is the most exciting part of every talk. So this is showing HSV. Um, oh. There we go. Cool. So here you can see we've got our red, green and blue channels, and we've got our hue, saturation and our value. So this gives you an idea of kind of the blue in the background.
So if you hold up a strawberry, will it circle it?
I actually have an oven mitt, which is the next best thing. So if you pick it up, you can wave it around and you can see that it's coloured in red. So as well as this demo, I have another demo. So this one here, particularly small, but if you have a well shaded enough,
Just on the front lights.
Now the
There we go.
Terminator gun aimed.
Why now it's tilting.
yeah. So you can play around with that, and that works relatively well, depending on the lighting. So that's why the robot had little lights either side of the camera. It's because lighting is a big thing, important thing. But, yeah. Cool. So oven mitt and or strawberry detector. Yeah. Cool.
Alright, thanks, Dennis.